Okay, so in this section of the unit, we're going to really apply the things that we did in 5.3 and 5.4 to going off and solving word problems. So that's what we mean by collecting data and modeling, because really a lot of things that are happening in the world, we can model with a sinusoidal function if it's repeating. So anything that's kind of happening, so this happens a lot of business where you have business cycles in terms of sales or something like that. So for example, we talk about maybe chocolate sales or pumpkin sales or something like that. Those happens very periodically. Even more recently, with the Perseverance landing on Mars, I would imagine there's lots of periodic functions that are involved in that, because just the way the planets in the solar system and astronomy works. The Earth revolves around the sun every 365 and a quarter days, so that's repetitive in terms of where the Earth is in terms of the orbit. Even the spinning of the Earth, that's going to be happening every 24 hours. So something is happening every 24 hours. So that obviously all affects our calculations on, when NASA is going to shoot the rocket off the Earth, and even Mars is revolving around the sun in a periodic way. In other words, it has a certain amount of days, we call it, that it goes around the sun. And so those calculations are needed in order to for the rocket or Perseverance to actually hit Mars, because we need to know the exact location where Mars is going to be. Thankfully, Mars rotates around the sun or revolves around the sun at a constant, at a regular interval. So periodic functions happen a lot, actually, when I think about it, in our everyday lives. And so here we could actually use sine curves or cosine curves to model behavior. In order to do that, we need to be able to come up with an equation. So that's why 5.3 and 5.4 are important. Coming up with an equation either from a description of a function or a graph. And sometimes when we come to the word problems, I still like to sketch a graph on the side just so I can get a visual what's going on. And when I get a visual what's going on, it's a lot easier for me to see the peaks and the troughs. More importantly, I can see that the equation of axes, and I can hopefully see the period a little bit better. So those are some of the key things that might be easier to see from a graph than opposed to a description, or in this case, what we have is a table of values. So in a warm-up, we're told that, it's a sine and cosine equation, so we know it's a periodic. In fact, we know it's sinusoidal. And here are some of the information that we're given. So one of the things that we could kind of pick off from the table of values is the peak. So we see that it's hitting 5 as a high point every time, and we could kind of assume that. It could be higher than this. That's not actually in the table of values. Sure, but I mean, that makes the question impossible. So you could assume in the table of values that we're given, the high points will be, the highest number will be the peak, and the lowest number would be the trough. So in this case, we have the lowest number, and that's going to be -1. And even the degrees that we're given in here, it's happening at a regular interval. So here they're reporting it every 30 degrees. So we could kind of see that this data should fall in line into a periodic function. Even here, even from the table of values, we could sort of pick off the period. So again, one of the things that I mentioned before was that we go from a peak to a trough, or trough to a peak. That horizontal distance is going to be half the period. Or another way we could actually see it, now that I just highlighted the peaks, let me highlight the troughs as well. So here we have the troughs as -1. In fact, there's only one, so we can't actually use the trough in this case, but we could use the peak to determine what the period is. So here we go from 10 degrees to 130 degrees. That's going to be the period of 120 degrees. I'm just going to do a quick sketch of this. That's why I provided this grid here. And also in the question, if it doesn't ask for one, you don't have to provide one. You don't have to create one. In the word problems, you probably rarely asked to do a sketch. But again, I encourage you to do a sketch to visualize what's going on with the problem. So every 30 degrees, this one's going to be tough to graph because the period, which is 120, and then we divide 120 to get the scale by 4 to get 30 degrees. But our marks, our peaks and our troughs don't exactly fall into that, so we just have to adjust a little bit on our graphs. So again, we're not looking for exactness. We're just looking for a ballpark graph to help me visualize what's going on. So at negative 20, I have 2. So maybe negative 20 is over there. Then at 10 degrees, I have 5. So 10 is just past 0. So maybe right there. 40 degrees, I have 2. So I see where the equation of axis is going to be actually 2. And then at 70 degrees, so just past 60 is negative 1. And then at 100 degrees, I'm at 2. And then I could kind of keep repeating. I can see it's repeating. So at 130 degrees, oops, that's not 180. That should be 120. So 130 degrees, it's 5, back at 5, and you can see the pattern there. So once I have really the first 5 spots, first 5 points, I can see what my sinusoidal curve is going to look like. Oh, I missed it again. Let me try this again. Oh, kind of stuttered there. But anyways, that's what it kind of looks like. That looks really ugly. But again, I have an idea what's going on. So I need to draw my equation of axes. It's 2, so I can actually calculate it. 5 plus, 5 minus a negative 1. Sorry, 5 plus a negative 1. So that's the average. Let me write it down. So here the equation of axes is going to be peak plus trough over 2, which is 5 plus a minus 1 over 2, which is 4 over 2, which is 2. So I can see in this line over here, that does cut it in half. My amplitude is going to be peak minus trough over 2, which is 5 minus a negative 1 over 2, which is 6 over 2, which is 3. And I can see that the horizontal distance here is 3. Sorry, the vertical distance there is 3. I get my K value, so now I know my period. So my K value is 360 degrees divided by the period. And here, that's going to be 360 divided by 120, which is 3. So here in our equation, we want the sine and cosine curve. So we could do it 2 ways to get the phase shift. So let's do the phase shift. I always choose the sine one first. If I'm asked for both, I do the sine one first, cosine one first, because cosine, we think about the parent function. When x is equal to 0, it starts at the highest point. So wherever the high point on my graph is, wherever I shift it left and right, that is the phase shift for cos. So for cos, so we could do it 1 or 2 ways. We could actually go back to the table of values and take the actual high points. So we don't actually need the graph for that. Here I can see the high points are at 10 degrees to the right and 130 degrees to the right. So either one of those be right. And you're just going to choose a smaller one. So this is actually 10 degrees to the right. So there's my equation for cos. Let me write this down first. G of x is equal to, so A is 3 times the cos, not sine, cos. My K value here happens to be 3 as well, times x minus 10 degrees. And the equation of axes was a positive 2, so it's plus 2. Well, to get the phase shift for sine, we can do 1 or 2 things again. With the graph, it's easier to see. Where am I going across, hit the equation of axes in our graph, and it's going up. And I hit at the very first one, which is minus 20. So maybe that's the one I'm going to choose. So here it's minus or 20 degrees to the left. So the equation for sine is going to be 3 times the sine of 3. I guess maybe I should use a different variable. Maybe I'll call this s of x. 3 times sine of, in this case, x. Since it's 20 degrees to the left, d is minus 20. So it's going to be plus 20 degrees, and all the other attributes stay the same. Okay, I could have chosen this point over here as well. So that was 100, I believe. Yeah. So how we could actually do this from the table of values is if we know what the equation of axes is. So in this case, we know it's 2. So where will we find 2? It's the next point higher or lower. So in this case, the next point, the next y value is actually higher. So we can see that the sine graph would be moving up, and this would be negative 20 would be the sort of the phase shift for sine. We hit 2 again, but the next next y value after that is actually down, so lower, negative 1. So we could almost kind of envision that, well, from 2, it's going down. This is not where a phase shift for sine would be. Likewise, once we hit 2 over here, it's going up, so that we can see that 100 degrees, which is this point over here, is also a valid phase shift. Okay, so this is really the skills of it, the heart of coming up with the equation. This was the table of values, but once we see a word problem, we're going to give certain pieces of information. We just have to map that. So our success criteria for today is we're going to use the sine and cosine functions to solve real-world applications involving periodic behavior. And in the most majority of the cases, in fact, all the situations in the examples we're going to go through today, we're not given the equation. So we have to come up with the equation before we could answer specific questions. So here's the first example, and it's the infamous Ferris wheel. Anything that goes round and round and round, we're going to see that that's sort of a repetitive pattern. So I'm going to read the problem first, and then maybe draw a quick diagram to help us visualize what's going on, and then we're going to map that diagram to a graph. So a group of students is tracking a friend James who is riding a Ferris wheel. Not important in terms of our equation, but just notice that it's a Ferris wheel. Help us envision what's going on with the problem. They observe that James reaches the top of the Ferris wheel as 11 meters high. So here, again, keyword there's top. We could recognize that, maybe I write the information over here. I'm really given the peak of our equation, that's 11, at 10 seconds. So this is important information. I'm not sure how I'm going to tie that in yet. But at 10 seconds, he's at the highest point. And then it says into the ride, and then reaches the bottom of the ride that is 1 meter above the ground. So again, there's the keyword there, bottom. So it kind of hints to me that's the trough. And it's 1 meter above the ground at 55 seconds. So given another time, how are we going to relate all this? What's happening here is a diagram, and excuse my art, but there's my Ferris wheel. And James starts on the ride somewhere, okay? We don't know where exactly. I could tell you it's not the top because he doesn't hit the top until 10 seconds. So assuming that the Ferris wheel goes in a counterclockwise direction or clockwise direction, chances are he may have started somewhere over here. Because 10 seconds in, he's going to hit the top. So there's the top. Well, there's the bottom of the Ferris wheel and there's the ground. So we know the ground is going to be at 0 meters. So we know that the bottom of the Ferris wheel is 1 meter. So the Ferris wheel, the bottom of the Ferris wheel is 1 meter above the ground. Well, the height of the Ferris wheel, the highest point up here is 11 meters. So he's going round and round and round. So what we want to do is create a function that determines how high he is. In other words, how high he is based on the time that he's into the ride. Okay, and notice that as he goes round and round and round, he's going to hit the same heights over and over again because he's going around in a circle. Okay, so that's what we're going to come up with a function to sort of model that. So I provided a grid here just to help us visualize what's going on. So here, notice that our independent variable is actually t. So we're not talking about degrees anymore. I think this is one of the abstract things that sort of confuse students, is that all along we've been talking about degrees. But now when we get to the real world problem, we're not actually measuring angles anymore, but we're having a variable that our other variable, dependent variable, is on this, where we know we get the same answer over and over again. So in this case, with the Ferris wheel, we know how high James is depends on how long he's been in this ride for. So in this case, we're using t into our sine and cosine function. Even though it's not degrees, we're just getting the value of sine and cosine based on that in order to solve our questions here. So here, and this is where I had in the chart here, my x-axis is actually time. So we're saying that 10 seconds in, so this is where the time is important now. We're saying 10 seconds in, he's at 11 meters high. Well, 0 seconds, when he starts to ride, he has to be below. I mean, because he's at the top at 10 seconds in. We're given more information at 50 seconds in, he's at 1 meter above the ground. So 55 seconds in, he's at 1 meter above the ground. So when you think about this a little bit, we're not given any more information. But think about how long is it going to take once he hits the bottom to get back up to the top. Well, because the Ferris wheel moves at a constant speed, that's why going around in a circle in the Ferris wheel, it's going to be periodic. So we know it takes him 55 seconds to go from top to bottom, and it's hinting at sinusoidal, but even you think of an application of Ferris wheel, if it's moving at a constant speed, it's going to take him the same amount of time to go from the bottom to the top. So here we're going to have to do, well, this distance here is 45 seconds. Because it took him from 10 seconds to 55 from top to bottom. Well, that means it's going to take him another 45 seconds. So what's 55 plus 45 is 90. He'll hit the top again at 90 seconds into the ride. So I could sort of guesstimate a curve, and it'll look something like that. Okay, again, not looking for complete accuracy, but here's an idea of what's going on so that I could, first of all, when I go off and calculate certain things, so here the peak is 11, the trough is 1. Maybe we can answer the period right away. So here the period is not talking about degrees, but it's talking about seconds. How long does it take him to do a full revolution on the Ferris wheel? So, oh wait, I'm just looking at the numbers. I missed it. It's not 90. 55 plus 45 is 100. So my bad. So it's 100. And the reason why I saw this right away, because I'm doing the period in my head. And really, what's 45 plus 45, or 45 times 2? That's 90. The period should be 90 seconds. In other words, it takes him 90 seconds to go once around this Ferris wheel. And so because he started, he didn't hit the top until 10 seconds in. He's not going to hit the top again until 100 seconds. So that's how I realized I got that point wrong. But in the end, as long as I get the period somehow, which is 90 seconds, the amplitude in this case is going to be peak minus trough over 2, which is 11 minus 1 over 2, which is 10 over 2, which is 5. So that implies my A attribute is 5. My equation of axes is going to be peak plus trough over 2, which is 10 plus 1. Sorry, 11 plus 1 over 2, which is 12 over 2, which is 6. So I'm going to graph that right away. And even though my graph was poor, I could kind of see that that is sort of the middle of the graph. So that implies that my C value is 6. Well, my K value is going to be 360 divided by my period. So in this case, it's 90. So my period is going to be, my K value here is going to be 4. 360 divided by 90 is 4. So how do we come up with the equation? Not leaving a lot of room here, so I'll just do it at the bottom. So if you're not told which one it has to be, whether sine or cosine, the easiest one is just to do the cosine. Here, where's the highest point? Well, the highest point is over here. What's the phase shift? What's 10 seconds in? So it's going to be 10 degrees or 10 seconds to the right. So my equation here is going to be g of x is equal to, my amplitude is 5. So I've chosen cos. And my k value here is 4x minus 10 degrees plus 6. All right, so there's my final equation. That's should get more working room for that. And in fact, we could answer some of these questions first before we actually got to the equation. So determine the time required for the Ferris wheel to complete one revolution. So one revolution is 1 cycle. So really, what's the period? In this case, as we said already, it's 90 seconds. What is the amplitude? Well, the amplitude we calculate to be 5. So how do we relate this to this situation or context? Well, if we look at our diagram that I drew, this really is the amplitude, right? From the middle, so this is really the middle of the Ferris wheel. We go up or 5, up, down, down 5. So this is really the radius. So maybe 5 meters. This is the radius. of the Ferris wheel. The equation of axes, we would calculate to be y is equal to 6. And so this represents, in this case, so we're looking over here, so this is the equation of axes. So usually the center of the Ferris wheel, right? You can think of it as the axle of the Ferris wheel. In this case, 6 is how high is it above the ground. All right, so in this case, the equation of axes represents the height of the center of the wheel. Or you can think of it as the axes above the ground. So here, this is why we need equation, because at the very end, really we want to know how high is James 90 seconds into the ride. Well, how do we do that? Well, this is why the equation we got is important. So the equation again we got was g of x is equal to 5 times the cos of 4 of x minus 110 degrees plus 6. So really we want to solve for g of 197. So just plug in 197 for x. So that's going to be 5 times the cos of 4 of 197 minus 10 plus 6. Running out of room here. We do this off to the side. So really we need to do everything in the brackets first. So 197 minus 10 is 187 times 4. So really you're going to do 5 times the cos of 748 plus 6. And we plugged all that into a calculator, so we do the cos of my answer, multiply that by 5, and then add 6. We're going to see that James is approximately 10.4 meters above the ground. Okay, I would write a proper therefore statement there, but I ran out of room. So that's how we answer that question. So one thing I didn't have a chance to really go over and emphasize is that this is not the only equation that we could come up with. We could have came up with a sine equation. So let's do a little bit of review. How would if I wanted to do a sine equation, how would I get that? Well, here my a is still the same. That's the s of x. Is 5. Now I'm dealing with sine. My k value is still the same because the period is still the same. We really need to find a different phase shift. So x something plus 6. So in this case, I could do a phase shift. I'm going to look solely to the right. So go along equation of axes. Where sine go up? Well, not there, but it goes up over here. So in this case, what is the x value over here? So we need to find the phase shift. So this is down over here. So one of the things we recognize in the periodic function, everything happens in quarters, in fours. So what's half of 45 is 22.5. So we know that that's a distance of 22.5 from here. This is also a distance of 22.5 from the equation of axes to the peak. And basically everything's chunked in 22.5. So here we got 55. That's the x value. So 55 plus 22.5 is going to be 77.5. So this is to the right. 77.5 degrees. So that would be another equation that we use. And if I plug in 197 into this equation here now, I'm going to get the same answer. So this is why we're saying that there's more than one equation, but they all map to the same graph, or we're all going to get the same answers to all of them. Let me just rewrite this because I really crammed that 77.5 in there. Let's clean that up. So minus 77.5 degrees plus 6. If we want to be really sort of explorative and taking some risk or really understanding this unit, I could have came up with another equation for sine, in that this would be reflected. So notice that when I hit the equation of axes over here and sine is going down, I could treat this as a reflection. So that'd be negative 5 sine. Well, here the shift is not going to be the same, but in this case it's going to be 10. So remember I said this was sort of chunked, into 22.5. So from here to here is 22.5. So this whole distance over there from is shifted is 10 plus 22.5, which is 32.5. So I could plug 197 for x into this equation. I would get the same answer. Okay, so that's the really cool part when we deal with sinusoidal functions. So that's that example. Hopefully we get a feel of what's going on, recognizing that given a word problem, I was really trying to get the peaks and the troughs in the period. And once I got that, I could sort of graph it or visualize it to see where the shifts might be. But I encourage you to, if you could draw a graph, that's going to help you determine what the actual shift is. Or if you're focusing just on the cosine curve or the cosine equation, the shift is wherever the maximum is occurring. Or, here's a hint, if we know where the bottom is, well, that's cosine reflected. So we can also determine where the bottom of the cos is and do equation with that, but as a negative reflection, as a reflection of the cos graph, which means that A is negative. So let's look at our next example. So another thing that sort of is repetitious in our world is waves. So waves is another popular question. So here at the end of a dock, we have high tide at 16 meters, and there was the highest wave, or highest the water is the high point. So I'm not talking about waves, I guess just talk about the depth of water is 16 meters. So that's the highest it gets. So hint, that's our peak. So I'll write that down over here. So our peak is 16. So it's recorded at 9 a.m. That might be important. And low tide at 4 meters is recorded at 6 p.m. So low tide, that's the lowest water level. So that's going to be my trough is 4. And that happens at 3 p.m. So what's the time? How many hours pass between 9 and 3? Well, that's going to be 6 hours. So we could assume that's going to hit high tide again at 6 hours from 3, which is going to be 9 p.m. So really, this is happening every 12 hours. I think this happens in the real world. I'm not a tide expert, but tides do happen now. We did go to Nova Scotia. We did visit, I can't remember where it was, the name exactly, but we did see the high tide and low tides. It was approximately 6 hours apart. Now, it wasn't exact. So that's the part of geography, or, I guess it's geology that I don't fully understand how this all works. Obviously, high tide revolves around the position of the moon to the earth, and because that's where the moon is closest to the earth, that's why we get a high tide. And when the moon is the farthest away from the earth, in some sense, that's where we get a low tide. So it's approximately 6 hours. So for simplicity, we'll keep it at 6, and we're going to repeat this every 12 hours. So basically, you get high tide twice a day and low tide twice a day. So we want to come up with a function to model this. So we need to in order to come up with a proper equation, we need a reference point. Okay, so notice that here in a reference point, height is obviously reference to how high the Ferris wheel is off the ground. Time was a little bit tricky. When does time actually start? In other words, what does time at 0 actually means? So in this case, we're talking about when James actually starts, or when the ride actually starts. So as soon as the Ferris wheel starts moving, we hit our timer, and that's where time is 0. So it would be an interesting question in this actually is, how high was James at the start of the ride? Well, we're plugging t for 0 in our equation. So in this equation, we want to determine, well, what are we referencing for time? So height is easy. It's reference to the ground, right? 60 meters above the ground, 4 meters above the ground. But in terms of time, so construct a model for the depth using a cosine function. So this one is requiring us to do a cosine function, but I'm happy with that. Cosine is easy. Where time is measured in hours past high tide. So 9 a.m. is a bit of a ruse here, not important. So we don't say like t is equal to 9. You can't have actually time for the actual clock time to be the variable. It has to be based on hours. But here t of 0 is actually high tide. So that's what this is applying over here, where t is equal to 0 is high tide. So in other words, We want a quick equation where it actually starts at height. Well, this one's actually really easy then. So let's do what we discovered the period. We said it was 12 hours, so 12. Peak and trough was 16, so let's do the amplitude. So amplitude is peak minus trough over 2, which is 16 minus 4 over 2, which is 12 over 2, which is 6. So that's my amplitude. My equation of axes is peak plus trough over 2. So 16 plus 4 over 2, which is 20 over 2, which is 10. So my amplitude is being 6. That implies my A attribute is 6. Equation of axes is 10. So that implies my C attribute is 10. Let's get my K attribute since I know the period. So K is going to be 360 divided by the period. So in this case, 360 is over 12, which is 20. So my K value is 20. And because we're starting at high tide at 0, and we want the cosine function, the phase shift is actually 0. So our actual equation here is g of x is 6 times the cos of, in this case, k is 20x. You know what? I'm going to come up with better variables. Let's not talk about t. So let's not talk about x. Let's talk about h. H short for hours. So how many hours after high tide will get the height? Well, H is kind of weird because H could be for height. So let me change that. Let's do time. Makes the most sense. Time. And really I shouldn't call this G of H, but we want to get the height. So maybe H of T. So the height of the water based on the time is this equation of 66 times cos of 20t. And my equation of axes is 10. So how high is the water 2 hours after high tide? Another way that we could have phrased this question is how high is the water at 11 a.m.? Because, well, when it's high tide, 11 a.m., so 9 a.m., 11 a.m. is 2 hours after high tide. So that's what we want that reference is after high tide. So it's actually 2. So in this case, we just want to figure out for h of 2. So 6 times the cos of 40. So 20 times 2 is 40 plus 10. Plug that into the calculator. So 6 times the cos of 40. And then we're going to add 10. And that's approximately 14.6. So therefore, the water is 14.6 meters high. All right, it makes sense. It should still be pretty high because it's only just after high tide, only 2 hours in after high tide, so it should still be pretty high. All right, so that's how we solve that problem. The next one is quite a bit tricky because it's not talking about heights anymore. So here we have a flagpole that goes back and forth. So it's going back and forth. So if I was to draw a little visual, there's my flagpole. Yes, sorry, that's the best I could do. Maybe put a ball on top of it. There's my flagpole. And it's going left and right. So this wind is blowing it back and forth. All right, so there's the ground. Which pushes it 5 centimeters to the left and 5 centimeters to the right from its rest position. So the rest position was when the flagpole is completely vertical. So in other words, it's moving 5 centimeters to the left and 5 centimeters to the right. And it does this 8 times per second. Okay, but you need to read carefully. It does what 8 times per second? It moves from left to right, or vice versa. In other words, it does this 8 times per second. Or really, we want to think about if you think about the period. In other words, how often? What's the full pattern? So I'm just trying to choose that color. So it goes here. It takes a certain amount of time. In fact, let's actually convert this 8 times per second to how long does it take it to do once, and that'll maybe help us see the math a little bit. So 8 times per second, that's actually pretty quick. So how long does it take it to do once? Well, that's actually going to be means that it does it in 1/8 of a second to do it once. Okay, so we would kind of to do reciprocal of that. So it basically takes 1/8 of a second to go this way and back. So that's what I'm saying. It moves from left to right. Oh, sorry, it takes 1/8 of a second. So I need to clarify this. It takes 1/8 of a second go from left to right. So it takes 1/8 of a second to do that. But then that's not really periodic. It needs to come back to its other position. So we're going to take another 1/8 of a second to go back this way. So what's the actual period behind this is actually 1/8 times 2, which is 1/4 of a second. Now it's going to take 1/4 of a second to go from one side to the other and back. Or really, you can think of it as, it's a little bit more complicated, but it's from rest position to one side to the other side, back to the rest position. Regardless of how we define that cycle, it's going to be, in this case, 1/4. So here we could say, I'm going to write the period is 1/4. But how can we model this, because it's not talking about height? So we're going to actually take a little different perspective on this. In that we could use positive and negative, not just for height, but direction. So positive, we could say that it's going to be left. And negative, we could say that's to going to the right. So when we say positive 3, that means it's actually 3 centimeters to the left. And we say negative 3, that's actually 3 centimeters to the right. Now, why did I choose left for positive? Because I kind of cheated and I went down to the actual modeling. Push it back 5 times to the left and then right. So here, we're actually given the description. So it's starting from the rest position and it moves to the left first. So I'm going to move positive first and then to the right. So how I would draw 2 cycles of this, it would look something like this. So that's 1, 2. Okay, how long does it take the whole time to go from one side to the other? Well, that's going to be 1/4. So what's half of 1/4? Well, that's sort of given to us already. It's an 1/8. And again, I'm going to mark the intermediate points in here, the times. That's going to be 1/16 of a second. And then 1/8 plus 1/16 is 3/16 of a second. Okay, so those are the intervals that we're getting at. So basically, we're saying at 1/16 of a second is going to be 5 centimeters to the left. And 1/8 of a second is going to be back to the middle. At 3/16 of a second is going to be 5 centimeters to the right. So I'm going to label that. That's 5. Oh, that's negative 5 and 5. And find 1/4 of a second, we're back to where we started, which is completely vertical. And then we'll continue on, and it's going to be going back to the left again. So in this case, my peak is actually 5. My trough is negative 5. So let me do those 2 quick calculations of my amplitude. Well, I can hopefully see the amplitude is just 5, but I'll do the calculations. Peak minus trough over 2. So that's going to be 5 minus negative 5 over 2, which is 10 over 2, which is 5. And then the equation of axes is peak plus trough over 2. So it's going to be 5 plus or minus 5 over 2, which is just 0. Okay, we see that really in the middle, that's where 0 centimeters to the left or right, that is actually the middle equation of axes. So here I got my 2 attributes already of A is 5 and C is 0. So now I know my period is 1/4. So I get my K value. So K is going to be period divided by, 360 divided by my period. So it'd be 360 divided by 1/4, which is the same thing as 360 times 4, which is, need to break out the calculator, 1440. So in this one, I'm actually going to choose a sine. So it doesn't say which one. So it's determine an equation that models the horizontal distance from breadth and sketch a graph. So in this case, because it's already starting in the middle, I don't want to deal with a phase shift. I'm just going to choose a sine curve. And this is another reason why I chose left as positive, because I want it, because it's moving to the left, I want positive to be negative. So therefore, it's just a no phase shift for the sine. So my equation is actually, I could name this P of t, where the position of the flagpole is based on the time, is going to be my A value is 5. So I chose sine. So there's going to be no phase shift. So it's going to be 1440 times t and plus 0. All right. So here, sorry, what I'm looking at. So there's my equation. We want to determine the flag position of the flagpole 0.2 of a second in. So here we just want to plug in the equation, 0.2 of a second. So B is we need to figure out P of 0.2. So it's going to be 5 times the sine of 1440 times 0.2. So just plug that straight into my calculator. 1440 times 0.2 is 288. So this would be 5 times the sine of 288. So take the sine of that and multiply that by 5. And I get negative 4.76 roughly. So what does the negative value mean? Well, negative value means it's to the right. So therefore, the flagpole is approximately 4.76 centimeters to the right. All right, so it's not below the ground. So you need to understand what a negative value means in this case. The next one is a bit tricky because now we're actually getting to the next part where we have to do solving a trig equation. But we need to determine the time which the flagpole is 3 centimeters to the left, moving towards the rest position. So a couple of key things there. One is the 3 centimeters. So on my graph, I'm going to plot where 3 centimeters to the left would be, and so that's really a positive 3. So that's where the flagpole is, say, roughly around 3. So where is it going to be 3? It's going to be right where it crosses that line. Y is equal to 3. And there's where's my answer 3? And we see that within one cycle, it happens twice. It happens twice. So we need to read the question carefully because which one are we looking for? It says moving towards the rest position. So when it's at 3 centimeters here, it's still moving to the left. So that's not the one that we want. This one over here, when it's 3 centimeters, is moving back to the rest position, back to 0. So this is the one that we want over here. Well, why are there 2 answers? Well, this comes back to our understanding of Unit 4. So how do we solve C? Well, here we're given an equation. Where's the position based on time? So we get our equation, 5 times the sine of 1440t. And then the position, in this case, is going to be a positive 3 because it's 3 to the left, is equal to 5 sine of 1440t. So we need to solve for t in this case. So I'm going to divide 5 on both sides. So I'm going to continue this up over here. So we see that sine of 1440t is equal to 3/5. So in order to get t, I need to do the inverse sine. But in order to do this, I can't do this first. Sorry, I can't do this first. So I need to solve 1440t. But really, I can only solve for alpha. So alpha is going to be the sine inverse of 3/5. Right? In order to get 1440t, and you decide, but we're not going to get the angle first. So let's come back to the previous. I can only get the reference angle. That's why we get the 2 answers. So what's the sine inverse of 3/5? So plug down my calculator. That's roughly around 37 degrees. So we see that 140t, well, again, it's not related to the angle though. So this is the part we need to sort of come back and says, well, there's two possible answers for sine. So we do my cast. Sine was positive in this quadrant and that quadrant. So that tells me that alpha is 37 over here. But that tells me alpha is 37 degrees over here as well. But this is I'm looking for the second answer. I'm looking for the bigger angle. So what does that make theta actually in this case? So that makes theta actually 37, 67. So 180 minus 67, which is 123 degrees. So we see that T, 140 is actually equal to 123. So in order to get T, we're going to take 123, divide by 1440, and that's going to be 123 divided by 1440. That's going to be roughly 0.08 seconds in. Okay, so it's going to be, it's going to take at 0.08 seconds for it to be 3 meters to the left, in this case, moving back to the center. Okay, so this last question is really tricky, only because we can't solve for this directly. We have to go back to a previous unit, and talk about really going to get the reference angle. And if the question was, well, if it was moving towards 5 points, then it was still moving to the left, then we would have said that this is not 123, but we're left at 67. Okay, so that was the other tricky part, was that we're not dealing with, we need to calculate for the reference angle, but we need to know which actual theta we're dealing with. And that's what we have to plug into the final equation of 140t is equal to what? In this case, has to be 223.